Welcome to this year's GS UK virtual conference. We've lost the E in a kind of Brexit move, so this is now GS UK. I'm very pleased to open the Db2 stream at this conference with somebody I've known for some years now from IBM, 40 years at IBM, but now with Triton and going from strength to strength. I like the way your bio says you retired on the 22nd of August 22, and then you're back with Triton in January 24. So short retirement and then back to full strength. So yes, great to have John Campbell up first session and presenting Db2 for zOS data sharing performance tuning. So we're just at 11:15, so I will open it up. Please, if you've got any questions, do put them in the chat, and every so often I'll take a pause and let John answer the questions. There's plenty to pack in, as always, with John sessions. So without further ado, I'll hand over to the man himself, John Campbell.
Thanks, Colin. You can hear me okay still, Colin?
I can. Very
Perfect.
clear.
Right then, so welcome to this session, which is going to be about data sharing performance tuning. In my previous life, when I was much younger, I was the performance team leader in Db2 performance team for the introduction of Db2 version 4. So if you do have any complaints about the performance of Db2 data sharing, I'm the one to blame. But I can tell you we worked very hard at the time during the duration of the version 4 life cycle and in the releases afterwards to deliver really good performance for data sharing. So let's look at the agenda. I'm going to make a brief introduction because I just want to share with you some previous experience prior to Db2 data sharing of other technologies that try to implement shared data and what the problems were in terms of them not being able to deliver, the performance expectations that our customers needed. I'm then going to give a short introduction as well about the Db2 data sharing architecture before I then deep dive first of all into global locking. We're going to have a bit of a deep dive inside the lock one structure, how it looks inside, global lock contention, and how about and resizing it, and giving you some rules of thumb about whether or not you've got problems to do with the lock structure. And then we'll switch topics into the group buffer pools, where again we'll have a deep dive into the structure itself, talk about reads, write, cast out, and then I'll provide you again with some rules of thumb for tuning and how to go about that tuning depending on what the constraints are. So if you have any questions as we go through, please put them in the chat window to Colin, and then periodically he'll interrupt me with some questions. So in terms of this introduction here, there were earlier what I call database clustering solutions, which is the idea of coupling multiple systems together to have shared access to data. And we'll talk about some examples at the end of this slide, but if we look back at them, so this is nothing to do with Db2 data sharing, this is what the previous implementations were about. There was excessive performance cost in terms of CPU cost and also not being able to meet the response time requirements. A lot of that performance problem was due to message passing. So there wasn't something like a coupling facility. So therefore, messages were being sent around the various systems every time a lock needed to be granted. Or if you had a piece of hot data and the data needed to be refreshed, then it involved message passing. Seriously degraded throughput and very poor scale out. These sort of systems might scale possibly to 2 or 3 systems, but when you try to scale out to beyond 2 or 3 systems, then performance was absolutely horrible. So the contributing factors were the global locking protocol was all about message passing. Even if a lock could be granted without contention, message passing was involved. When there was what I call, hot data. In any application system, there's usually some data where there's heavy inter-system read-write interest on that page of data or set of pages. And without a coupling facility with data in there, then unfortunately this resulted in message passing between the members to tell the members that had stale versions of the page to have it refreshed. And the other thing with these earlier implementations, there was no pay-as-you-go protocol. In other words, it assumed everything was inter-system read-write shared, and therefore paid the penalty of the message passing. And if we look at some examples of these, the first one was IMS database data sharing Mark 1, which was prior to the data sharing implementation in version 4. And I worked on one of those early customers, which is using Kix with IMS DB data sharing. And quite honestly, when we put two systems together to start with, we got less throughput out of two being put together than we did out of one, which is obviously horrible, isn't it? And then you can look at Oracle RAC cluster. Now, this solution is really good for consolidating lots of small applications. And often when you look at the implementation of Oracle RAC clusters, that's usually what they're doing. And usually they're in small cluster sizes of 2 or 3 systems in a cluster, but not well suited when there's large applications with heavy inter-system read-write interest. Now here on slide 4 is a picture you've seen many times, I'm sure, which is why you're on this session today. I can remember using this back in 1994 when version 4 came out, but simply to illustrate that the main thing here is the coupling facility, which you would always have two, because, you know, like with Noah and the Ark, one of the benefits of data sharing and parallel sysplex was about continuous availability, and that meant redundancy. So it's strongly recommended you always have two coupling facilities. And inside there is there's one lock structure for the group, one system controlled area, which is used for cross-system information. And then there could be a group buffer pool backing up each of your local buffer pools. And all of the members have equal priority. There's no particular preference. Ideally, they should be cloned with the applications replicated. And all the system data, the catalog and directory, the logs, and also the application databases are all inter-system write shared. So now, as promised, I'm going to deep dive into, first of all, the lot 1 structure. There's just one lot 1 structure for the whole group. And if I try and use a pen here to illustrate this, what we've got here is two particular, maybe I'm going to regret I ever did this, but I am going to regret the fact I ever did it. So anyway, on the right-hand side is a picture of the lock structure, very simplified, but there are two parts inside that lock structure. You've got a lock hash table, which consists of lock table entries. And those lock table entries, individual ones, can either be 2 bytes, 4 bytes, or 8 bytes, depending on the number of members in the data sharing group. But for the purpose of this illustration, we're using 2-byte lock table entries, which means that the size of the data sharing group can be up to seven members. And within those 2 bytes, you've got an exclusive byte, which is byte 1. And then in the second byte are a set of individual bits. And this information is used for Db2 to determine whether or not there's lock contention. So whenever there's the first update lock that lands on a particular lock table entry, then that exclusive or global byte is filled in at the front. And when a member comes in with either read or write access, any other member, then the respective bit is actually flipped. So that's what that top part is. The second half is the bit at the bottom, which is called the record list table, sometimes called the modified lock list. And this contains all the locks associated with database modifications. So read locks are not stored. It's just the updates locks associated with insert, update, and delete that are put in there. So what's it used for? The main thing, and it's really one of the crown jewels of data sharing, is that coupling facility is used to quickly detect whether or not there's global lock conflict. So by simply making Db2 through the IRLM, making a quick call to the coupling facility, it can quickly determine whether or not a lock can be granted without contention. So for example, whenever a lock is taken, it goes through a hashing algorithm to determine which of the lock table entries it should be put there. And basically, if the exclusive byte is not filled in, let's say it's 00, then you know there's no inter-system read-write interest. On the other hand, if the exclusive byte is filled in and one of the other bits is set on, then that means there's inter-system read-write interest. So in most application systems, the vast majority of the locks can be granted without contention. And you certainly would like that to be the case, otherwise performance wouldn't be very good. So the advantage here of this fast inter-system global lock detection, it just takes one call to the coupling facility, and no message passing is involved at all. Message passing only gets involved when inter-system lock contention is detected. Also, it provides a solution for cross-system or inter-system page latch contention. There are certain pages in Db2 that Db2 takes a page latch on instead of a lock, such as when you're using row level locking, on the space map pages, and on the index leaf pages. So as part of the data sharing implementation, when an object is group buffer pool dependent, then Db2 takes a page P lock on those types of pages, and those locks are propagated into the coupling facility. So therefore, Db2 is using the page P lock and the lock contention mechanism to provide a cross-system equivalent of a page latch. It's also used for dynamic tracking of inter-system read-write interest because it's a pay-as-you-go system. So Db2 has a hierarchical locking model where you have a parent lock and a child lock. And Db2 only propagates the child locks once it's known there's inter-system read-write interest on the parent locks. So when a Db2 members start up and they touch a particular object, then the lock is propagated to the coupling facility. And if there's contention detected, then the exits will get involved and determine whether or not it's group buffer pool dependency, and then start propagating the child locks. Now, what's the significance of this record list table? And the significance of this is that when a member goes down, the other members in the data sharing group know that member's gone down, and then what they're going to do is race through that record list table, converting all these modified locks to retain locks. So this is used as a way of protecting uncommitted updates when a particular Db2 member crashes out. Now, the size of that lock one structure is defined in what's called the CFRM policy, the Coupling Facility Resource Manager policy. And we have a couple of examples here. So the first one here is when the init size is 512. Can I just ask you to hold on a second, please? Hold on.
Just while I've got a minute, just if you do have any questions, put them into the chat and I'll ask them as we go along, or indeed at the end. But yeah, we try and answer questions as we go along. There's nothing at the moment, so don't be shy, stick them in the chat. Should play some music now. Yeah, obviously someone's knocking on the door and John's gone to answer that. That's the beauty of virtual conferences. You've got people knocking on the door and delivering things. Here we go.
I'm very sorry about that, Colin. Somebody was trying to break into my house.
Oh, right.
Anyway,
it's always good to sort those sort of things out.
Yeah, I almost headbutted him. In fact, I could have been arrested. But anyway, to go back to this, it's the lock one structure, as you've seen, has two parts. And in that first example, the init size is 512 meg. And what Db2, or should I say IRLM does, he tries to create a 50-50 split. So in this case, it's very simple because 512 meg is a power of 2. So you end up with the lock hash table for the lock table entries at 256 meg and the record list table at 256. Now in the second example, the init size is not a power of 2. And in fact, if you look at 768 megabytes, it's just beyond the halfway point between 512 meg and 1 gig. And once you go over that point, it gives bias to the record list table. So you can see here that the LTEs are 256 and the record list table has now gone to 512. So the space here is now biased towards the record list table. And as we'll talk about later, if you have long-running jobs, long-running URs that don't commit very often, doing heavy updates, then there's always a danger of running out of space in the record list table. As I also mentioned, the size of the LTEs, lock table entries, depends on the number of members in the data sharing group. So you can see here, if you go to, if you've got somewhere between 8 and 23 members, then the lock table entries jump from being 2 bytes to 4 bytes. In case it's on your mind about how this works, then if you don't specify an LTE parameter in the IRLM, as soon as you start the 7th member, he will dynamically rebuild the lock structure to allow for 4-byte lock table entries. So let's first of all talk about a problem if you're short of these record list entries, because you have long-running URs that don't commit very often. So Db2, or should I say IRLM, pops out various messages depending on the space usage in terms of record list entries. So the first one is just an information message, the DXR 170, and you get these alerts at 50, 60, 70% space used. But once you start getting to 80% and beyond, you start getting the DXR 142 easy message. Now, these you need to monitor for. So once you get the 80% full message coming out, then data sharing is not, there are no restrictions on data sharing function and performance. It's just simply telling you that the memory is on its way to reaching the critical threshold. At 90%, now you're in some trouble, because now only must complete type of requests that require lock structure memory are processed. So by must complete, it means things like they've got a unit of work that's either in rollback or in commit processing. And at 90%, then basically any request that requires lock structure memory is denied, and you've got an out of lock structure storage error. That's what it means. So let's now move on to global lock contention. And bear in mind, I'm trying to net this down so it's easily consumable for you. In the top left-hand side here is an extract from the data sharing logging section of an OMP report. And I've highlighted the key fields in there in terms of you've got the number of locks, changes, and unlock requests, the number of locks that were converted to go async for whatever reason, and then it tells you the number of suspensions. IRLM global lock contention is true application level lock contention. XES global contention is really a form of false contention simply because the system lock manager, which is called XES, inside zOS, only understands a limited number of lock states, and therefore you can end up with some false contentions. And the last one, the false contention counter, is when you truly have false contention, when you have different resources, different pages, different rows, whatever, landing on the same lock table entry. So you've detected the IRLM working with the coupling facility will have detected contention, but once it's gone through the message passing, it finds out that there's the two or more different resources have landed on that resource. So false contention, in fact, is an expense. It's delivering no benefit to you whatsoever. So on this slide 8 here, I'm offering up a couple of rules of thumb for you. The first one is the global lock contention rate, which OMP calculates for you anyway, should be less than 3 to 5% of the total number of requests. Now, how that calculation is performed is actually underneath the actual rule of thumb for you there. So it's simply it's calculating the total number of contentions by summing up the suspends for IRLM, XES, and false. It's then adding up the number of XES IRLM requests, which are the sync ones, which are a combination of lock, change, and unlock, plus the asynchronous ones. So through that calculation, you'll then get what is the global contention percentage. Well, basically, anything less than 3%, you've got better things to do. Everything's okay. Think of it as being a green condition. Between 3 and 5%, it's a boundary condition. Let's call it amber. And anything above 5% needs investigation. Because if you have excessive global lock contention, that will involve message passing, and that will impact the cost of your applications, the cost of the system, and also its ability to scale out. And in the second half of slide 8 is a rule of thumb offered here for false contention. And in this case, then, the amount of false contentions should be less than 1 to 3% of the total number of XCS IRLM requests. Now, let's now talk about resizing that lock1 structure. What would cause you to want to resize it? Basically, one reason would be if you have false contention, a high rate of false contention, or it could be a shortage of record list entries. Now, false contention is, as I've discussed on the previous slide, is when you get 2 or more resources landing on the same lock table entry. So if we assume that the hashing algorithm used by Db2 is a balanced algorithm and gives you a really good spread of the resources over the lock table entries, then by doubling the size of the lock table and thereby the lock table entry table, then you should be able to halve the false contention. Now, in a perfect world, that would be the end result. If you doubled the size of the lock structure, and specifically within that the lock table, then you would halve the false contention. But that's not always the case, but it's certainly the tuning action you would first take. There are historically some types of locks which don't hash very well and don't end up with an unbalanced hashing algorithm. And sometimes there may be a defect in DB2 or a design constraint in DB2, such as there was a red alert early in the life of version 13 to do with UTS partition table spaces, to do with using relative page numbers, and IBM corrected the hashing algorithm. Or anyway, the second problem is just simply shortage of record list entries. Either because you've got a single long-running unit of recovery that take lots of locks without committing, or there are lots of concurrently updating applications which in total have blown away the size of the record list table. So if the shortage of the record list entries is the problem, but the false contention is okay, then what you can then do is think about using the LTE option in the IRLM startup proc to specify for, depending on the size of the lock table, how many entries you want. So at the bottom of the chart here, on the very left-hand side, the init size is 1024 megabytes, so it's a power of 2, and there's a 50-50 split between the lock hash table and the record list table. Now, if you go to the blue square there, now the init size is not a power of 2, it's 1280. But if you specify a lock table entry of 256, that will mean the lock table entry is 512, and the record list table would be the remainder, which is 768 megabytes. So using the lock table entry here is a way of giving more space to the record list tables. In the second box there, that's gray there, if the init size is 1024, which is a power of 2, normally there would be a 50-50 split, but because the LTE has been set to 125 in the IRLM startup proc, then you end again with the lock hash table being 256 meg, and the record list table becomes 768. Now, if you do change the LTE parameter in the IRLM proc, or you use the IRLM modify or the zOS modify command to set the LTE, that in itself doesn't implement the change. You actually need to rebuild the lock structure. So use the setxcf command to dynamically trigger the rebuild of the lock structure on the fly. Normally that takes a tiny number of seconds. Very rarely does it take more than a tiny number of seconds, but it's something that can be done on a live system. Now let's talk about global lock contention further. It really is important for your applications to use a lightweight locking protocol. And by locking protocol, I mean isolation level and to exploit lock avoidance. So those lock avoidance algorithms that came in version 3 and were enhanced further in version 4 are all about trying to reduce global lock traffic, specifically for read-only SQL. There's no lock avoidance for insert, update, and delete locks. So the benefits of lock avoidance are improved concurrency, reduced lock and unlock activity and the associated CPU overhead, decreasing the traffic to and from the coupling facility, and also minimizing the impact of retained locks. Because if you're not taking a read lock, then you won't collide with the retained lock that's there. So what does, a lightweight locking protocol mean? It means using isolation cursor stability with current data no on your static SQL. Or if you're using dynamic SQL, then you want to actually set your isolation level to be CS, and for the associated null ID package for cursor stability to have been bound with current data no, or the other option is to use an isolation level of UR for uncommitted read. Other aspects here are is to commit frequently to reduce global lock contention and to improve the effectiveness of global lock avoidance. Prior to version 12 of Db2, all it took was one long-running UR somewhere in the data sharing group, and that would fix the global commit LSN value that was used for lock avoidance. So that meant that just this single long-running UR would cause global lock avoidance to degrade. Now, with the advent of version 12 of Db2 and Buffer Manager tracking the 500 worst cases, this means that, if you do have the long-running URs, then locks against those objects will obviously see their lock avoidance degrade. But for the other applications which are behaving very well, they will see improved global lock avoidance. Another point to bear in mind is to avoid serialization points. And an example of this is where people have maybe a single row table, which is used as a counter, as a way of generating a unique identifier. And those always become a serialization point. And also an availability issue should a particular member go down. So it's much better from a performance viewpoint to use an identity column or a sequence object with a cache option to provide a much more efficient way of generating that unique identifier. And also exploit table and index partitioning. And normally people think about using partitioning as a way of, based on the size of the table. But in fact, having wide partitioning on a table can also be beneficial from a global lock contention viewpoint, especially related to indexes. Because for every index partition you have a separate index B tree. And provided the new keys that are being inserted are spread somewhat randomly over the key range, then that would allow, by having more index B trees, there would be less chance of having contention on what's called the index tree P lock. Let's now switch topics within here and talk about P lock negotiation. So again, there's a section here of an OMP report which shows the negotiation. By the way, there's not much negotiation on here. It's just simply indicating where there's contention and where things have moved around. So you have the page set partition lock, first of all, which is on the parent locks, which is used to track inter-system read-write interest. So there is a negotiation that takes place whereby what's called the P lock exit gets driven. And this is how an object either goes into or out of group buffer pool dependency. Then you have the page P lock negotiation, which is the key point, which is to do with row level locking, the space maps, and the index leaf pages. So here you can see where they are negotiations. Is it at the page set partition level? Is it at the page level? Or is it something else? Now, one of the things that's nice in the Db2 statistics trace is that when you've got excessive page P lock negotiation, you can see where most of those contentions are coming from. So in the picture there, again, an extract from an OMPE report, you can see in the bottom left-hand corner there that when there are page P-lock negotiations, you can see how many were on space maps, how many were on data pages, and how many were on index leaf pages. So that will help you identify which is the constraining factor, the most significant factor, and determine what your tuning action might be. So I do have some comments here on slide 12 about for insert intensive workloads where you end up with high page P-lock negotiation on space map pages, you might want to consider using member cluster. And later down, I've mentioned about if you have relatively small tables and you're using row level locking, then if you are ending up with lots of page P-lock contention on data pages as a result of using row level locking, you might want to consider on small, medium-sized tables, switching to max rows 1 lock size page to simulate the row level locking and reduce space map contention. And finally, at the end there, if your problem is to do with the indexes, then you might want to consider either reorganizing the indexes more frequently, with or without the table space, to re-establish the distributed free space of %free page, or actually increase the values of %free and free page to try and dilute the hotspots. Alternatively, what you could also consider with moderation is increasing the index page size without using index compression as a way of reducing the number of index leaf page splits. And very quickly on slide 13 here, this is just an extract again from the OMP, but this time it's the accounting report, simply saying from an accounting perspective, you can see, for example, in the class 3 suspensions, whether your weights are related to global lock contention or page latches. And then in the various sections inside the accounting trace and report, you can see what the global contention rate is for that application. And when on the buffer pool side, when there are page P-lock negotiation, whether it's dominated by space map pages, data pages, or index leaf pages. If you want to try and identify the hotspots from a locking perspective, then one thing to do for a short period of time is to start a performance trace. And in this case, it's performance trace class 30, which is a user-defined performance trace, and collect these IFC IDs. And then this is an example from OMPE. You can actually set it up to run the locking report. And what it will do is create you a .csv file that you can then load into a spreadsheet tool like Microsoft Excel. And then once it's in Excel, you can then manipulate it in sheets and, for example, identify the resources which have the highest number of contentions or those resources that have the highest lock wait time. So with that said, I'd now like to switch over to the group buffer pool structures. And in the group buffer pool structure on the right-hand side, you've got two parts. You've got a group buffer pool directory area where there's one directory entry for each distinct page in the data sharing group. So for example, if the page is in member A's buffer pool, member B's buffer pool, and in the group buffer pool, you just need one directory entry. But on the other hand, if all the pages are different, you'll need one distinct directory entry for each distinct page in the group. And the second half of the group buffer pool structure is that when pages are updated and they have to be written to the group buffer pool, then the data is actually stored in the group buffer pool, which means that if there's heavy inter-system read-write interest in terms of update on hot pages, then when a page is invalidated, it can be quickly refreshed from going to the group buffer pool as opposed to reading the new version of the page from disk. So what happens is that when a page is read into a local buffer pool, that page is registered in a directory entry in the appropriate directory entry in the group buffer pool. When a page is updated and pushed into the group buffer pool like P2 in this example here, then the coupling facility control program will use the information in the respective directory entry to send a cross invalidate signal to the other members who have interest in that page, causing the bit in what's called the local cache vector to be invalidated. And the next time the buffer manager tries to access the page, it will test the respective bit in that local cache vector associated with that page, and if it's been flipped to indicate it's invalid, it will try and refresh it from the group buffer pool. So to summarize this, the group buffer pool structures are used to register buffers for potential cross-invalidation. When pages are written to the group buffer pool, cross-invalidate signals are sent to other members who have interest in the page, causing them to ultimately refresh the page. There's a special hardware structure that Db2 uses to test the bit vectors when a buffer has been cross-invalidation, and hopefully from a tuning perspective, that when a page is cross-invalidated, there'll be a fast refresh of the page from the group buffer pool. So when it comes to cross-invalidations, there are two reasons for the cross-invalidations. The first one is perfectly normal. You can't avoid it. It's just part and parcel of having active inter-system read-write interest. But the second one is one that needs to be avoided. This is when there's a shortage of directory entries. And in other words, one particular member wants to register a page in the group buffer pool, but there's no available directory entry for it to use. So what it's going to do is the coupling facility control program is trying to steal a directory entry associated with a page which is read-only. Now, when a directory entry has to be reclaimed, that's going to result in extra CPU and I/O overhead, extra access to the CF, and synchronous I/O read as well. So that may mean you have to read the page, having read a page into the buffer pool, because the associated directory entry is reclaimed, the page has to be reread into the group buffer pool. So first rule of thumb here is that by using the display group buffer pool with the type gcon, you can see how many reclaims you have for directory entries and whether they resulted in cross-invalidations. And in this case, you've got a perfect answer of near zero. May not be absolutely zero, but we want a very tiny value in terms of reclaims and cross-invalidations. When it comes to group buffer pool reads, what you want to tune for here is that when there is assuming you've dealt with the first issue first, you've eliminated the unhelpful cross-invalidations, then when it comes here, what you want to see when it comes to sync read XI, you want to get a very good read hit ratio, or conversely, a very low miss ratio. And the rule of thumb here is that the sync read XI miss ratio should be less than 10%. And if it's more than 10%, you should investigate why that is the case. It may well be that the group buffer pool is too small, or the cast out is not happening. Well, ultimately it means that the group buffer pool is too small. So you really want to try and design this so you get a fast refresh of a hot page, index or data page from the group buffer pool. When it comes to writes, pages can be either written synchronously or asynchronously. Change pages are written synchronously at commit, and when there's a p-lock negotiation. They're written asynchronously when you've got a deferred write or a system checkpoint. Now, one thing that was implemented in version 12, I think, or maybe 11, was this write around mode. And this is trying to reduce the number of instances when the group buffer pool is filling up with dirty pages. So this mechanism only applies to the pages that are written asynchronously to the group buffer pool. And this particular function basically ping points in and out. So we just take one example at the group buffer pool level threshold, which is GB pool T. If it goes above 50% used across the buffer pool, then it starts cutting in and start writing these asynchronous pages directly to DASD. And then it tunes out again once it's come down to 20%. So what DB2 is doing with this mechanism is basically ping-ponging between GBP cache change, which is normally how it works, to GBP cache none. And when it's in trouble here and this mechanism cuts in, it's not writing the change pages directly to the coupling facility. It's writing them to the DASD instead. In terms of cast out, I don't want to dwell on this too much, simply to say that the cast out thresholds are similar to the local buffer pool deferred write thresholds. So the class T threshold is basically at the object level, and that's checked every time there's a write to the particular page is pushed out for that object to the group buffer pool. So it's the most efficient way of triggering cast out. GB pool T is the horizontal threshold, and that's checked frequently based on a timer, a 1 second timer interval. So these are the thresholds, both class T and GB pool T. By reducing those thresholds down, that will trigger more frequent cast out. So as transactions and data volumes grow, the group buffer pool can become more stressed. And then you can start to see messages like the DSNB325A message, indicating a critical shortage of space. And when the condition is relieved, you get the DSNB327I message telling you there's now adequate space. So the reason for implementing that group write around feature, excuse me, was to try and reduce the number of instances of the DSNB325A and to reduce the time gap, should they occur, between the DSNB325A message popping out and the Db2 327I message saying the condition will be relieved. And usually this problem is usually caused by update intensive batch jobs running maybe concurrently and or utilities running against group buffer dependent objects. Now shortly I'm going to talk about a function called XES alter, which can help in this situation, but it's meant to be a conservative feature and will not react in a radical sort of way. So the next rule of thumb here on the group buffer pool is that memory shortages can impact application performance and ultimately, if they're not dealt with, become a serious availability issue. So I've got some examples here of output from the display group buffer pool command and also from the statistics trace. And in each case, you see a value for write failures. Now, a write failure doesn't mean it's terminal. It just means it tried to write to the group buffer pool and there was no space available. Doesn't mean it actually failed, because what Db2 will do is retry multiple times. Of course, ultimately, after 8 minutes, I think it is, then what will happen is that page will go on the LPL and be unavailable and hence become an availability issue. So the rule of thumb here is that write failed no storage should be less than 1% of the total number of change pages. A useful command here is to do the display group of pool gdhl star gcon, and that way you can see information about the size of the structure, where it's grown to the maximum size, and find out very quickly whether you've got write failures or shortages of directory entries. So a little bit I've only got a tiny number of minutes here, so I'll have to paraphrase some of this. The group buffer size is defined in the CFRM policy. The size is the maximum size that it can grow to, and the init size is the size that's allocated. And there were some changes made in Db2 version 12, which are important. The default ratio, which is the ratio of counts of directory interchange pages, the default became 10, and the maximum ratio was increased from 255 to 1024. Now, I will have to not be able time to go through all of this, but here we have an example of the output from that display group buffer pool command, and there are two buffer pools that are in trouble here. Group buffer pool 2 and group buffer pool 8K0. Now, in the case of group buffer pool 8K0, the allocated size has already reached the maximum size. And in the second half here, you can see that both group buffer pool 2 and group buffer pool 8K0 both have directory entry reclaims. And in case of group buffer pool 8K0, it has write failures. So what I've got, and I'll have to paraphrase it because of time here. What I've got here is some targeted tuning. So the first one is if the group bubble has a large number of directory entry reclaims, but there's no minimum write failures. And what I've got here on this slide 25 is the my advice on tuning and what the action should be. So I'll leave you to study that later. Targeting tuning number 2 is when you have a large number of write failures. And again, this is the recommended tuning, and these are the changes required. Then I want to talk about briefly about XES alter. This is an autonomic piece of function provided by XES working with the coupling facility that tries to avoid structure full conditions and tries to avoid directory entry reclaims. So, the recommendations here on how to set it up are provided on the second half of slide 27. So what it will try to do is to either grow the size of the structure until such point it reaches maximum size, which is called size, or it will adjust the ratio. So again, I've got an example here that if you're starting to see that once the init size or the allocated size has reached the size, this is the advice then on resizing the size of the structure in the policy, the maximum size, and the ratio. Right. And the last thing on slide 29 here, if you want to increase the size of your local buffer pools, that will increase the demand for your group buffer pool, not because of the change pages, because you need more directory entries. So again, here is the advice about the tuning and also on the changes required. So with that said, I've managed to finish, I think, almost on time, Colin. I apologize for rushing the last few slides here, but hopefully people will be able to study those slides and then follow the recommended changes. Do we have any time for questions, Colin?
I think so. Yeah, that's brilliant timing. So thanks very much for that, John. Yeah, if there's any questions, I can unmute you or put them into the chat. In fact, I can offer to unmute everyone. So if anybody's got a question, please shout now. There you go. I think you should be able to unmute yourselves. If you can't, put it into the chat and I'll shout out the question. Do we have any questions? It's all gone very quiet.
Everybody's being very shy today.
Yeah, I guess it's the first session, but there's plenty of information packed in there, John. As always, I've written some useful notes. There's a few things I want to check out, so I'll take them back to base and see what's what. So thanks very much. Last call for questions. No, nothing. Okay, thanks very much, John.
Yeah, and thank everybody for attending my session. Enjoy the rest of the conference. Take care.
Thanks, John. Time for a quick lunch, and then we'll be back on the Db2 stream at 12:30 with some system profiling stuff from Keziah Knopp. So see you then, hopefully.
Take care,
And
everybody.
thanks.
Bye-bye. Thanks, Colin.
Cheers.
Bye.